Yesterday we talked about rings. We talked about different types of rings. We talked about rings with unity. We talked about commutative rings. And we talked about units, that is elements in rings which have multiplicative inverses. Today we are going to discuss integral domains. Now before we talk about integral domains, we need to define a zero divisor. So first let's go to the concept of a zero divisor. A zero divisor is a non-zero element A of a commutative ring R such that we can find another non-zero element B in R such with AB equal to 0. Now an integral domain is a commutative ring with unity and which has no zero divisors. Let me repeat. An integral domain is a commutative ring with unity and no zero divisors. That is, it is commutative with respect to the operation of multiplication. It has a unit element, an identity element with respect to multiplication, and it has no zero divisors. A field is a commutative ring with unity in which every non-zero element is a unit. Let's discuss a few examples of integral domains. We are going to look at a few examples, both of sets which are integral domains and which are not integral domains. First, we are going to talk about this ring of integers. That is an integral domain. Next, we talk about the ring of Gaussian integers. The ring of Gaussian integers is a set of all numbers of the form a plus bi, where a and b are integers. That is also an integral domain. If you look at the set of all polynomials with integral coefficients, that is also an integral domain. Next, we talk about the set of all numbers of the form a plus b into root 2, where a and b are integers. Again, we find that is an integral domain. If you look at the set Zp of integers modulo p, where p is a prime number, we find once again that is an integral domain. However, when we take Zn, where n is not a prime number, then it is not an integral domain. If you look at the set of all 2 cross 2 matrices with integer entries, that is not an integral domain. And the external direct product of the integers with itself is not an integral domain. Now let's look at a few results regarding integral domains. Now the first rule is the cancellation law, which is probably the most important rule as far as an integral domain is concerned. Suppose I take 3 elements a, b and c in an integral domain. Then if a is not equal to 0 and if ab is equal to ac, then b is equal to c. Let me prove that. Suppose AB is equal to AC, then A into B minus C is equal to 0. We have already been told that A is not equal to 0. So therefore B minus C is equal to 0 because we are talking about an integral domain where the product of two numbers can be 0 only if either one of them is 0. Since A is not equal to 0, B minus C is equal to 0 and therefore B is equal to C. The next result says that a finite integral domain is a field. Let D be a finite integral domain with unity 1 and let A be any non-zero element of D. We have to show that A is a unit. Suppose A is equal to 1, then it's its own inverse. If A is not equal to 1, then we can consider the sequence of elements A squared, A cubed and so on. Since D is finite, there must be two positive integers I and j, where I is greater than j, such that a raised to I is equal to a raised to j. Now I can use the cancellation law and say that a raised to I minus j is equal to 1. Since a is not equal to 1, we know that I minus j is greater than 1 and hence a raised to I minus j minus 1 is the inverse of a. The next result says that for every prime p, Zp, the ring of integers modulo p, is a field. Now for that, first we will prove that Zp is an integral domain and then we will use the result that every finite integral domain is a field and say that Zp is a field. So first let me prove that Zp has no zero divisors. Of course I know that Zp is commutative and has a unit element. So let me first prove that Zp has no zero divisors. Let if possible a and b belong to Zp such that a into b is equal to 0. Then I know that AB is equal to some multiple of P. for some, that is AB is equal to P into K for some integer K. Now by Euclid's lemma, P divides A or P divides B. Thus in ZP, either A is equal to 0 or B is equal to 0. Hence we get that ZP is an integral domain. Since every finite integral domain is a field, the result follows. Next we are going to define the characteristic of a ring. The characteristic of a ring is the least positive integer n such that n into x is equal to 0 for all x in R. If no such integer exists, we say that R has characteristic 0. The characteristic of R is denoted by char R. Now what do I mean by saying n into x is equal to 0? I simply mean that x plus x plus x plus x n times is equal to 0. The next theorem says that if R is a ring with unity 1 and if 1 has infinite order under addition, then the characteristic of R is 0. If 1 has order n under addition, then the characteristic of R is n. Let me prove that. If 1 has an infinite order, then there is no positive integer n such that n into 1 is equal to 0. So R has characteristic 0. Suppose 1 has additive order n. Then n into 1 is equal to 0 and n is the least positive integer with this property. Hence for any x in R, we have n into x is equal to x plus x plus x n times, which I can write as 1 into x plus 1 into x plus 1 into x n times, which I can again write as 1 plus 1 plus 1 plus 1 n times into x. So that is equal to n into 1 x, which is equal to n into 1 we said is 0. So 0 into x is equal to 0. Thus R has characteristic n. The next theorem says that the characteristic of an integral domain is either 0 or it is prime. Let me prove that. Suppose 1 has order n which is not equal to 0 and suppose that n is s into t where s and t lies between 1 and n. Then I can write 0 is equal to n into 1. Now that since n is equal to st, I can write it as this is equal to st into 1 or s into 1 into t into 1. That since we are doing all this in an integral domain, either s into 1 is equal to 0 or t into 1 is equal to 0. But we know that n is the least positive integer with the property that n into 1 is equal to 0, which means that either s is equal to n or t is equal to n. Thus n is prime.